Hello, this is Mr. P, and today we're going to learn about inverse trigonometric functions. And the way we're going to do that is we're going to start with the definition, which can be a little confusing the first time you see it. Looking at sine, we have y equals arc sine of x if and only if sine of y equals x. And arc sine is the way we say the inverse trigonometric function, the inverse sine, or in other words, there is an alternative notation, which is y equals sine, which looks like a -1 power, but it is not a -1 power. It actually has to do with the inverse function, just like the notation for f inverse of x. So this would be the inverse sine. So arc sine or inverse sine, those notations mean the exact same thing, which is it's an inverse function, so we switch the role of the x and the y. Notice how it's not y equals sine x like we're used to, it's sine y equals x. And the same alternative notation for cosine and tangent would be inverse cosine and inverse tangent as well. Now for the meaning, this is where we want to make sure we have a clear meaning here. And with the original function, the original trigonometric function, we have to understand the role of the input in the output. So x being the input, this function is saying, if you give me an angle, because this input is an angle, if you give me an angle, then the sine function will tell you the length of the segment that represents the opening of that angle. So the output is the length of a segment. So input an angle, you output a length of a segment, which is a value. And we're reversing that for the arc sine or inverse sine. For the inverse function, we're saying you give me the length of the segment, and I'll tell you what the angle is that has that value as a sine value. Or in other words, for arc sine, what you say in your head is the angle whose sine is x. So when you see this notation, or the arc sine notation, you ask yourself the question, what is the angle whose sine is x? And it's the same corresponding questions for cosine. You say, what is the angle whose cosine is x? And what is the angle whose tangent is x? That is literally the meaning of this notation. Now with the angle, when we say angle, there are some things you to be aware of with the angle. First of all, it must be measured in radians. In order for this concept to work, we're talking about angles measured in radians. And it must also be within the restricted domain of the function, which of course leads to the question, what is the restricted domain? The restricted domain is a way that we can create a one-to-one function. Now if we look at another inverse function relationship here, this is our exponential function. This particular one is e to the x, our base is e. This is a function. Notice how it does pass the vertical line test. And it is also what's known as a one-to-one function because it passes the horizontal line test as well. Therefore, it does have a true inverse function, which is the logarithmic function. And so this one is the natural log of x. Notice how this one also passes the vertical line test as well as the horizontal line test. So geometrically, if you take the exponential function and reflect it about the line y equals x, then you will get the logarithmic function. Reflecting it about the line y equals x is geometrically the same as switching the roles of x and y in the function. So these two functions are inverses of each other. Now if we look at our trigonometric functions, we have sine, cosine, and tangent are the ones we're going to be looking at. Notice how we have a little bit of a problem here with the sine. The sine function is a function. Notice that it does pass the vertical line test. However, it does not pass the horizontal line test. So if you were to reflect this about the line y equals x, you will not have a function. So what we can do is mathematicians then have agreed to take just a portion of the domain that would give us all of the possible y values. Now we could have taken this portion, or we could have taken this portion, but in general we wanted an interval that captures all of the y values that's closest to the origin. So for sine, that interval is from negative pi over 2 to positive pi over 2. That interval will capture all possible y values on the sine curve, and we'll capture them only once. So if we were to restrict it to just this segment, just this curve part of the segment, then we have a one-to-one graph that we can then find an inverse for. So the restricted domain for sine is simply going to be from negative pi over 2 to positive pi over 2. Notice how it does include the endpoints because we do want the minimum value and the maximum value to be present in our list of possible values. So if we were to restrict the domain of sine to just this interval, then we can create an inverse function. Likewise with cosine, I want to represent all of the possible y values, but only once. So looking at the graph here, that can happen from 0 to pi is the interval that is closest to the origin. And for that, it also does include the endpoints, because we do want that maximum value and we do want that minimum value. So that would be our restricted domain for cosine. For tangent, if we look at just the branch that goes through the origin, that's all we would need for all of the possible y values. Notice how this one does go up forever and down forever. Or we say it increases without bound and decreases without bound. But for this one, you do have to be careful about one thing. The interval from negative pi over 2 to positive pi over 2, for that one we do not include the endpoints for tangent. Notice how there's no or equals to, because those are actually asymptotes. The tangent of pi over 2 is undefined. It would not be on the graph, so therefore we cannot include it as an endpoint. But as long as we restrict our functions to these domains, then we can create inverse functions. And let's take a look at those. This is the inverse function of sine, the inverse function of cosine, the inverse function of tangent. Or we like to say arc sine, arc cosine, arc tangent. Now notice how this function is not periodic. It does have a beginning and an end. The domain and the range have been switched from the previous function. So if we look at sine, notice how the restricted part of the sine function, the domain was from negative pi over 2 to positive pi over 2. Well, that becomes the range of the inverse function. And also the range, which is from negative 1 to positive 1, the y values is range, the range of the sine function becomes the domain of the inverse function. So we're switching the roles of x and y, or geometrically, if we take this portion of the curve and we reflect it about the line y equals x, we get this curve. Now notice with our meaning, if we were reading a point on the curve, such as this point, we would say the sine of pi over 2 is 1. So the inverse would say the angle whose sine is 1 is pi over 2. Notice the difference in meaning there. I'll say that one more time because that was sort of important. The sine of pi over 2 is 1 is how we read this graph. And here, the angle whose sine is 1 is pi over 2 is how we would read this graph. Now we do have to be careful that these are not periodic, so they don't go on forever. For example, let's say we were asked to find the arc sine of 5. Then looking at the arc sine graph, this would be saying the angle whose sine is 5. So we'd say the angle whose sine is 5, and over at 5 there is no graph. Therefore, it is undefined at that point. There's no angle that when you take the sine of it, it will return a value of 5. So therefore, that one is undefined. So be aware of the possible restrictions that would cause you not to have a value. All right, let's look at how we're going to use these inverse functions. First of all, we're going to be finding the exact values. And when doing this, we want to realize the meaning behind it, and we also want to create a proper visualization that's going to make these problems a whole lot easier. And what I found through experience is for values that are the special values within the special right triangles, for those I want to draw the triangles. And for the quadrantal values, I like to look at the graph. I found that to be the easiest visualizations. So looking at the first one, we want to know the exact value of the arc sine of -1/2. And when you see this notation, in your mind you should be thinking, well, what is the angle whose sine is -1/2? That's literally what that notation means. The angle whose sine is -1/2. So if we look at the triangles, because that is one of the special values, then first thing I want to realize is that the value is negative, which means we're not in quadrant 1. And in the restricted domain, if we actually look at our restricted domains again, one thing to point out about these is notice how the restricted domain for sine is -π/2 to +π/2. That represents quadrant 4 and quadrant 1. For cosine, it's 0 to pi. That represents quadrant 1 and quadrant 2. And for tangent, same as sine, it's quadrant 4 and quadrant 1. Those are where we want to draw our triangles. So coming back to our idea here, what's the angle whose sine is -1/2? We're not in quadrant 1, so we're in the other quadrant within the restricted domain of sine, which is going to be quadrant 4. So I draw a triangle in quadrant 4, which means my angle is the reference angle in that triangle. And for the restricted domain of sine, we measure that angle as a negative angle. Remember, it's -π/2 to +π/2, which is quadrants 1 and 4. And now I just, if I take the sine of this angle, I will get -1/2. So sine is opposite over hypotenuse. And I can get that by doing a -1 in the opposite and a 2 on the hypotenuse. And hopefully then you would recognize 1, 2, square root of 3 is a special right triangle. It's a 30, 60, 90 triangle. So we have our theta, our angle, is opposite the smallest side of the triangle, which makes it the 30-degree angle. And don't forget, it's negative, so it would be -30 degrees. So therefore our answer in radians, because it does have to be in radians, is going to be -π/6, which is the angle whose sine is -1/2. Now that's a lot of thinking to go through that, but as long as you're making the visualizations, then these problems are going to become a lot easier. So let's look at a few more. Here I want the angle whose sine is √3/2. Well, notice how our values are positive, so that means we're going to be in quadrant 1, which makes this one nice and easy. So my theta is going to be the angle inside the triangle that touches the origin. And then I want opposite over hypotenuse to be √3/2. So hopefully you recognize the 1, 2, √3 triangle, which is 30, 60, 90. This time theta is opposite the square root of 3, which makes it the 60-degree angle. And in radians, 60 degrees is π/3. That is the angle whose sine is √3/2. Now if we look at the third one, I want the angle whose sine is 2. Well, that's actually never going to happen, because notice how this is not one of our special values that we recognize. This is one of the quadrantal or other values. So for those, I'm going to look at the graph itself. This is the first cycle of the graph of sine, which you should be very familiar with. You'll be using this little graph a lot in the future. And if we think about anywhere on the sine curve, it never goes up to 2. So the angle whose sine is 2, that just doesn't happen. Therefore, this value is undefined. So be aware of the possibility of undefined answers. All right, let's look at a couple more examples. Here we want the arc cosine of √2/2. And for that, notice my values are all positive, so I'm definitely in quadrant 1. The inverse trig functions, whenever they're positive, you're going to be in quadrant 1. If they're negative, then they're going to be in the other quadrant within the restricted domain. Now, hopefully, this is our theta, which is our reference angle. hopefully if you recognize that square root of 2 over 2 is the same thing as 1 over the square root of 2 after it's been rationalized, then that can make it easier to say that adjacent over hypotenuse is 1 over the square root of 2. And then you recognize that this is a 1, 1 root 2, which is a 45, 45, 90. And therefore our theta is 45 degrees, but in radians, because our answer does have to be in radians, would be pi over 4. So our cosine of root 2 over 2 is pi over 4. The angle whose cosine is root 2 over 2 is pi over 4. All right, for part B, I want to first notice that negative 1 isn't one of the special values, that's a quadrantal value. So therefore I want to use the graph rather than drawing a triangle. So looking at the graph of cosine, remember cosine starts up at the maximum and then goes through the cycle like this. It is negative 1 when it reaches pi, when it reaches halfway from 0 to 2 pi. We have 0, pi over 2, pi, 3 pi over 2, and 2 pi. So this is asking what is the angle whose cosine is negative 1. Well, as we see from the graph, that just happens to be at pi. So therefore our answer here would be pi. And we can move on to the next one. Here I want the arc tangent of 0. That is the angle whose tangent is 0. Again, this is a quadrantal value, so I want to look at the graph of tangent. And that first cycle of the graph of tangent looks like that. And the question is, where does tangent equal 0? Well, it equals 0 right there. And the angle that would be 0. That would be 0 radians. And the last one finally is the angle whose tangent is negative 1. Now, when you first see this, you might think that negative 1 is a quadrantal value, but it's actually not for the tangent function. Negative 1 is one of the special values for the special right triangle values for the tangent function. So we are going to draw a triangle. Now, it's negative, so it's not in quadrant 1, so it's in the other quadrant for tangent, which would be quadrant 4. Remember, for sine and tangent, they're quadrants 1 or 4, where cosine is quadrant 1 or 2. So here we have quadrant 4 triangle. Our theta is in our triangle, touching the origin. And in order to get a tangent, which is opposite over adjacent, that means my opposite would be 1, my adjacent would be 1, negative 1 over 1. That would give me a tangent of negative 1. And hopefully you recognize 1, 1 root 2. Notice how the negative side had to be on this leg because this is our down direction. So 1, 1 root 2, we have a 45, 45, 90 triangle. So this is 45 degrees, but measured in the negative direction because it's from negative pi over 2 to positive pi over 2. So that gives us a negative 45 degrees, which in radians would be negative pi over 4. Okay, now we're going to go through some properties that can help save some time. And there are a few restrictions on these. Oh, wait a minute, we have some more example problems before we get to those. Looking at the first one here, we have arc sine of 1/2. That means the angle whose sine is 1/2. You should recognize one of the special values. It's positive, so we know we have a triangle in quadrant 1. We have our angle theta. Sine is opposite over hypotenuse, so opposite would be 1, hypotenuse would be 2. Hopefully now you recognize 1, 2, square root of 3 is the special right triangle we're talking about. That's a 30, 60, 90. Theta is opposite the 1, which is the smallest length, so it means it's the smallest angle, so it's the 30-degree angle, which in radians would be pi over 6. For part B, we have arc sine of 0. Well, 0 is one of our quadrantal angles, so rather than drawing a triangle, I'm going to make the graph. This is the graph of sine. And the question is, where is it 0? Well, it's 0 here, or it's here, or actually even here. So it's 0 in many places, but remember, we want the angle that's within the restricted domain, which is negative pi over 2 to positive pi over 2. So this one is the only one that is within the restricted domain. So therefore, it would be 0. 0 is the angle whose sine is 0. For arctangent, we're looking at the angle whose tangent is root 3 over 3. Again, everything's positive, so we're going to be in quadrant 1. This is one of our special values. Hopefully you recognize that square root of 3 over 3 is equal to 1 divided by the square root of 3 before you rationalize it. So therefore, with respect to this theta, tangent being opposite over hypotenuse, opposite over adjacent, means we're going to have 1 over the square root of 3, and that fraction will become root 3 over 3 after you rationalize it. So now we recognize 1, 2 square root of 3, 30, 60, 90 triangle. I'm opposite the 1, so therefore I'm the 30-degree angle, which again is pi over 6. Notice how it's the same exact triangle that you had for the first one. And you'll find yourself drawing the same triangle over and over in many cases. So the arcsine of 1/2 is equal to the arctangent of root 3 over 3. And then for the last one, the arctan of -1. Again, 1 or -1 is not a quadrantal value for tangent. It is for sine and cosine, but not for tangent. So we are going to draw a triangle. It's negative, so we're not in quadrant 1. So that means we're in quadrant 4. Sine and tangent are 1 or 4. Cosine is 1 or 2. So we're in quadrant 4, which means our theta will be measured negatively as a negative angle. And in order for opposite over adjacent to be -1, then my opposite would be -1, my adjacent would be 1. That would give me that ratio. So hopefully we recognize 1, 1, 1 root 2, which is a 45, 45, 90. Therefore, our angle here is a negative 45 degrees, or in other words, a negative pi over 4. Okay, now we're going to get into some properties. And the inverse properties are going to be good time savers, but they do have some things you have to be careful of. We can get some good cancellations. If you're taking the sine of an arcsine, they can cancel out, or if you're taking the arcsine of a sine, they can cancel out. But there are some restrictions. There are some conditions that must be met. Now they give them to you here, but these can be a little confusing. What it boils down to is you either have the inverse function inside or you have the regular function inside. And remember, we do these things algebraically. We do the insides first, the inner parentheses first, order of operations. So rather than try to memorize these as intervals and apply them to each of these, there's a much simpler test. You want to ask yourself, if you have the arcsine, or if you have the inverse function, this applies to all three of them. If you have the inverse function inside, then you ask yourself whether or not this is defined, if it's possible to take that inverse function. If it is possible to take the inverse function, then these two can be canceled out, and it's simply x. That makes it pretty easy. Or if you have the regular function is the one that's on the inside, like with these three, then the question you ask yourself is the argument of that function, is that angle within the restricted domain? If it's within the restricted domain, then these two cancel out and you have simply the y value, or the angle. If it's not within the restricted domain, then we'll see in an example, you need to find a coterminal angle that is within the restricted domain, and then you can make your cancellations. So you need to rewrite the expression if this is not within the restricted domain. So again, these rules only work if it's possible to take the inverse function and if your angle is within the restricted domain. If you always think about it like that, then you don't have to memorize these intervals. So definitely be careful of the intervals. Those are the two questions you're going to ask yourself. For example, let's say we want to know the arcsine of the sine of 3 pi over 2. Well, 3 pi over 2 is not within the restricted domain of sine. Remember, it's negative pi over 2 to positive pi over 2. This is outside of that range, so we can't use this little shortcut. So how we would normally have to do it is we'd have to go ahead and take the sine of 3 pi over 2, which is -1, And then we ask ourselves, what is the angle whose sine is -1? And if we do that properly, we find out the answer is -pi/2, which is within the restricted domain. And that does not equal the original angle, which means if we were to use this property, we would have this wrong. So you can only use this property if the angle is within the restricted domain, or if the inverse is on the inside, then it has to be able to actually take the inverse. So let's see a couple examples of these, of course. Okay, looking at the first one, we have the tangent of the arctangent of -5. Well, for tangent, notice how the inverse function is on the inside, so our only test is whether or not it's possible to take the arctangent of -5. Well, tangent, if you think of the graph of tangent, goes up forever and down forever, so any value is possible for tangent. So here, I can take the arctangent of -5. It is possible to take the arctangent, so therefore I can use the property that these two cancel themselves out, and my answer is just 5. Makes it nice and easy. For the second one, however, it's not going to be so easy. I would like these to cancel out. However, this angle here, 5π/3, and again, we have the normal function is the one on the inside, so we have to make sure the angle is within the restricted domain. 5π/3 is not within the restricted domain of -π/2 to +π/2. So therefore, if we think about the angle 5π/3, this would be the angle 5π/3. We want the equivalent angle that is within the restricted domain. And in quadrant 4, within the restricted domain, we measure those angles negatively. So this would be the equivalent angle. So whether I go 5π/3 in this direction or whether I go π/3 in the negative direction, in either case I end up at this terminal side. So therefore the sine of that angle and the sine of this angle will have the same value. These are coterminal angles. So they will have the same values for all of their trig functions. So here, I want to rewrite the original expression. Instead of sine of 5π/3, I want it as the sine of -π/3. Because this value and this value will have the same magnitude. So here, now that I've rewritten it where this is within the restricted domain, I can use the property that cancels these two out, and my answer is just -π/3. And if we look at the last one here, the cosine of the arc cosine of pi, our only restriction here, our only question to ask ourselves, because the inverse is on the inside, so we want to know, is this possible? Can we take the inverse cosine of pi? So the angle whose cosine is pi, well, if you think of the graph of cosine, it starts at a maximum of 1 and gets to a minimum of -1 and always stays within that range. Pi is just the numbers, 3.14159, etc. So at no time will the curve of cosine ever get up to a value of 3. So therefore, we're going to have we're going to have something where we can't take the inverse function. Therefore, we can't use our shortcut, and even furthermore, it's undefined because we can't do what's in the inside anyway. So the first one, we were able to use the property to make it nice and simple. Second one, we're still able to use the property as long as we rewrite the angle as a coterminal angle that is within the restricted domain. And in the third one, if this is undefined, then you can't do anything with it. All right, let's look at one other thing that can happen. Notice how there's tangent and arctangent, sine and arcsine, cosine, arccosine. You can also do ones where you're taking the tangent of an arc of some other function or cosine of an arc of some other function. You can mix and match them. As long as you have the inverse one on the inside, the inverse function on the inside, then we can actually reason through these problems even though we don't know what the arc cosine of 2/3 is. I have no idea what the arc cosine of 2/3 is, but I know it's an angle. And that's the key understanding to be able to do this problem. So the angle whose cosine is 2/3, it's just an angle. Let's call that angle theta. Because the question doesn't really ask for what is the value of theta, it asks for what is the tangent of theta. So if I can draw a representation of theta and then use that drawing to tell what the tangent of theta is, then I've solved this problem. So the angle whose cosine is theta, now this is a positive value, so we're in quadrant 1. Then this would be our theta. And although I don't know what the value of theta is, I know that if I have a triangle where the adjacent is 2 and the hypotenuse is 3, then I would have an angle whose cosine would be 2/3. So this is a right triangle, so we can use the Pythagorean theorem to find the other side. It's not one of our special right triangles, but leg squared plus leg squared equals hypotenuse squared. So 3 squared is 9, minus 4 squared, 2 squared, which is 4, 9 minus 4 is 5, so this would be the square root of 5. So now that I have a visual representation of theta, I can answer this question, because it's asking for what is the tangent of theta. I still have no idea what theta is, but it doesn't matter, because the tangent of theta is simply opposite over adjacent, which is root 5 over 2. So we're able to answer this question even though we don't know what the arc cosine of 2/3 is. And let's look at another example of the exact same thing. Arc sine of negative 3/5. I have no idea what it is, but since it's just an angle, the negative argument tells me that is not in the first quadrant. So within the restricted domain for sine, it's going to be in quadrant 4. And we're going to measure that angle in the negative direction, because it's negative pi over 2 to positive pi over 2. So here we have sine is opposite over hypotenuse. Hypotenuse is always positive, so it'll be negative 3 over 5. And using the Pythagorean theorem, or hopefully you recognize a 3, 4, 5 triangle. In either case, you find the length of the other side, and now you have everything you need to find all of the trig values of that angle. So again, what is the arc sine of negative 3/5? I have no idea, but once I make a visual representation of it, I can see that the cosine of that angle theta, so the cosine of theta is simply going to be adjacent over hypotenuse, which is positive 4/5. And we're done.